And first thing you want to understand about Stokes theorem is it's pretty much just like Green's theorem. Except with this. Okay. And the picture brings theorem. We have an integral around the boundary of the region. And it's related to an area that by the fact that the difference in what you get on this part of the path and what you get in this part of the path depends first on the length of the path and then on the distance, the wide distance, let's say from here to here, and the wide derivative of your function. Okay, without going into detail, just kind of reminding you of that picture. This is a circulation. Okay. If your vector field has components that match up with these directions in the right way, then you have circulation around the boundary. Okay. Now, as you know, circulation is related to curl. Curl is a measure of circulation. Okay. So we can say that the not being specific, you say the path integral around here. Path integral isn't zero, then your field is tending to circulate around this field. Okay. At every point, circulation is measured by the curl. If you integrate the curl over the whole region, got total circulation, same as if you integrate the function over the path. And we drew a picture where if you have for general region, take it up to the sub-region. Each sub-region has a circulation around its boundary. The circulation of adjacent regions, the circulation over these boundaries will cancel out unless the region is boundary, in which case circulation on this part of the path is equal and opposite between here and here. That's about circulation on this part of the path is again equal and opposite between these two adjacent boundaries, but you're left with the circulation around the boundary. We talked about that in some detail. So we're not saying okay. With the total circulation within the region, then becomes the same as circulation around its close boundary. Okay. Well, that works in 3 dimensions. Well, it works for surface. Okay, this is Green's theorem is just in the plane. Okay. Stokes theorem applies to any surface. As long as the surface is orientable, not too weird. And your vector function, of course, has the appropriate characteristics, and if they go into too much detail on that. I'd love to know all the detail. Kind of confining myself to what my son does. Person. Ever get over this code problem in the pipeline, I'll say having mercy. But this give you enough to go on. Okay. And everybody's looking at engineering. It's really important tool in engineering, and the finer points of the proof usually don't impact the engineering. Although you do have a job. Okay, so to get the general idea about the same that okay. The integral of dot d has to round a curve. Closed bound. Double integral over the region. For the curl now. I'm going to say dot the vector dA, yeah, but it's going to do. Yeah, it's just your normal times your area. Okay. And it's calculated as cross product. You parameterize your surface. Do the cross product of the TU cross TV or whatever it is, vector times your DU DV. Okay. And it gives you this. Okay. It gives you the but these across TV DU. Okay. Now the whole technique of being able to set up the interval. At least one of these intervals, and then you know the other. Okay. So if you can integrate the curl of alpha over your parameterized region, then you already know which integral is. Or the case of Green's theorem, which is you integrate the curl inside here. Okay. And then that has to be the curl around the top. I think the line that will go around the top. Sometimes, and I think you experienced this with the Green's theorem, it's either difficult or impossible to do one of those two intervals. It'd be impossible to do the interval around the interior, but you can do the interval around the boundary, so you know what the interval around the interior is without actually having to calculate. Vice versa. Maybe the interval around the interior is easy, but the boundary is so weird, or it doesn't match up well with the function. Can't find a way to integrate. Okay. Do one of the intervals, not the other. Okay. Let's say F equals gradient of some function F. Okay. Some function little f. What's the interval gonna be?